In the last few videos, we've been developing the concept of the electric field, and to date, we have been visualizing the electric field by drawing maps where we attach vectors to specific points. However, we've seen that these diagrams can get fairly cluttered and have arrows crossing all over each other. There is a convention due to Michael Faraday, a very amazing character that we will meet more later, called electric field lines that allow us to draw electric fields diagrams that are much less cluttered. So the idea goes like this. Rather than drawing vectors, you draw entire lines that you attach arrowheads onto to give you some sense of direction. So these would be our electric field lines. Then if I want to know the electric field at any particular location, the electric field vector will be tangent to the lines. Now if we don't, so let's start with one that's on the line right here. The electric field vector here would be tangent to the line. Now if it isn't on a line, that's okay. You can have as many lines as you want. This is an abstraction. So you just kind of imagine what a line would look like that would fit between these. And you draw it tangent to that imaginary line. The other rule is that the strength of the electric field is proportional to the density of the electric field lines. So here, where the lines are packed closer together, you would draw a longer electric field vector. And out here, where the lines are spaced relatively widely apart, you would be drawing shorter electric field vectors. And this has the advantage that we don't have arrows crossing all over each other. So you can just look at the lines and then say, oh, I need to know the electric field vector at a particular point. And you can use these rules that the direction is tangent to the line and that the length of the electric field vector goes as the density of lines in the area. But it gets better. It turns out that there are rules for how to draw these electric field lines. And if you follow the rules, you can estimate the electric field anywhere without actually doing any math. Well, I guess technically you are doing math, but it's being done graphically. So I'll go ahead and state the rules, and then I will do an example of this. So when you're drawing lines, they always start on positive charges and they end on negative charges. The number of lines entering or exiting a charge is proportional to the charge itself. If you turn out to have excess lines, they will head radially go to or from infinity. I'll make that clearer in the example. And the last rule is that the lines can never cross. So in addition to those, there's actually a whole elaborate lore surrounding what if you have lines that are perfectly horizontal or perfectly vertical. My approach to that is to just avoid them altogether. And then you won't have to pay attention to those elaborate rules. So let's do an example here where I have a charge negative q right here. And then over here, I have a charge plus 2q. Actually, I want the charges to sit a little closer together. There we go. And I want to draw the electric field lines. So when I'm drawing these, I recommend that you choose the number of lines. I usually like using multiples of 4 for symmetry reasons. So I will decide in this case to associate 4 lines with a charge of q. So this means that here we will be having 4 lines that will be entering this charge negative q. Since this charge is double that charge, this means that I'll have 8 lines that are leaving. Oops, that one's not too good. That are leaving radially out in the immediate neighborhood. And what's going on here is that if I'm right next to a charge, remember we figured out if you're right next to a charge, then that charge is the only charge that matters. We know the electric field vector would be heading straight away there. So in the electric field line always has to be tangent to the vector. So the lines have to leave out radially in the immediate vicinity of your charge. And now what you do is you connect the lines and you figure out how to connect the lines in a way that they can't cross. So, oops. Actually, red is good. So there's one, and we draw in an arrow going from positive to negative. There's another one, positive to negative. And this one's going to do something like that. And this one's going to do something like that. Now, there's no particular reason why I chose to do 4 lines per q. I could have done 8, 12, whatever. It's just I'm not much of an artist. And so I chose 4 in order to minimize the drawing I had to do, and it would be good enough. Now these 4 excess lines have to head off radially toward infinity. So that's because if I'm far away, then it's that headlight trick again, where these two will look like they're stacked on top of each other, and far away it effectively will look like a single point charge. So I expect that these lines will have to curl away. Oops. So that they're heading off kind of radially. Now, if I want to know the electric field vector anywhere, I can just follow our rules for interpreting the lines. So if it's right here, the electric field vector will be quite strong because the lines are packed close together, roughly tangent to the line. So at that location, it looks something like that. Let's say out here, the field is quite weak. The lines are really far apart. And again, it would be tangent to the line, but we draw a short arrow to get our electric field vector over there. We can see right here in the immediate vicinity of the charge, we do have an inbound electric field vector here. But if I'm far enough away, it's going to be a weak outbound vector. So there's some point in here where the electric field is 0, which makes sense because although this is the weaker charge, you're closer to it. So there's got to be a balancing point. If you're close enough, this charge will dominate and the electric field will point inward. If I'm far enough away, then the fact that I have more charge here more than makes up for the extra distance. And so then the electric field vector would have to point out. And that is really pretty much all there is to it. Just one quick note for a particular pathological case. So let's imagine that you have two positive. You could have the same thing if there are two negative charges. Let's say they're both plus Q, like so. Now here, because of our dictum that the lines can never cross, let's go ahead and this time we'll use 8 lines per 2, 3, 4, 5, 6, 7, 8. Yeah, something like that. So this time we'll use 8 lines per and put them in here. 2, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there we go. So these do about what you'd expect. They'd head radially out. These will head radially out. These would head radially out. But here, these guys here, they have to start hooking over and heading away. And this is again because of our rule that the lines can never cross. And the lines can never cross because if they did, that would mean at some location the electric field vector was pointing in 2 different directions at once, which makes no sense. Okay, so my art here is absolutely atrocious. Let me try redrawing this one line here. Maybe they'll make it a little better. That's about as good as I can get. So you would think right here, when you're drawing this, you can see, well, there are lines in the area. So you might be tempted to think that the electric field strength right there is something. But actually, right at this particular point, the electric field strength is 0. Right at the dead center between the 2 charges. And this is just because this one is making a downward contribution, that one's making an upward contribution. If these are equidistant and the charges are the same, the contributions are the same, and it cancels. So if you see a whole bunch of lines all desperately avoiding a specific spot, the electric field at that spot is likely 0. Alrighty. So we will be using this tool going forward. It is a fantastic tool for being able to estimate electric field strengths before you actually do the hardcore math on it. So in the next video series, we will be doing more with electric fields. Catch you on the flip side.